Okay. So until now, in our lecture series, we have assumed a very ideal memory. That is, all memory access takes like one cycle. But assumes and if there is a unlimited size, then the number of cycles it takes more. Why? Because searching the requested data and transferring it back to the CPU. So then if the size of memory is supposed to reduce, then searching the requested block of memory is takes less time. That means it motivates that design a very small memory so that that will improve the memory access time. So that means if you look at this, yeah, let me just quickly get into this. If you look at this case, that the motivation gives that designing a small sized memory and accessing the data from small sized memory that we called caches. So in computer architecture, almost everything is cache. Like registers or a cache on variables, that is software managed one. I, that is the size of the registers is like in our discussion we looked at 8-bit registers, 16-bit registers, and 32-bit registers. Okay, but in generally in the modern computers, the size of registers are also increased. So the next level cache is a L1 cache. So this we have seen the L1 cache, how it is helped to give the solution for structural hazards in the pipeline. The next level memory is level 2 cache memory. That is second level cache, a cache on this memory. So that memory is a cache on the disk. Okay, so L1, L2, L3 cache and the memory that is on the disk tape. So then the translation-lookaside buffer is also a cache and page table, that TLB we call, and the branch target buffer and branch target address buffer, which we discussed in the speculative executions, that's also a cache. So that's why we say that in modern computers, almost everything is a cache for the storage. So the most processors today have three levels of caches. That is level 1, level 2, and level 3 of caches. Why? Because based on the size of the processor die, based on the size of these caches also to place on the processor die, one major design constraint for cache is their physical size. As size increases, these cache memories can be going away from the main core of the processor. As the size is limited, then these smaller size caches are closer to the functional units, that is arithmetic and logic unit. So, however, they used DRAM memory here, DRAM cells are used of the modern processors for embedded processors, like they use the SRAM also. So most importantly here is the L1 cache, which we discussed. So this L1 cache is to solve the structural hazard. It is divided into two parts, that the L1 cache for instruction memory and L1 cache for the data memory. So while designing the pipeline data path design, we look these two. So the typical size of this L1 cache is 64 kilobytes for a normal computer. So this 64 kilobytes is partitioned into two, that is 32 kilobyte of instruction memory and 32 kilobyte of data memory. So to avoid the pipeline structural hazard, these L1 caches are usually partitioned. So as bigger caches are too slow to access and will be physically difficult to accommodate on the chip. So then they will be too far away from the computational logic like ALU. Then the next level cache is L2 cache. These L2 caches are slightly further away from the CPU or ALU unit. Like if you take the arithmetic and logic unit here in the processor, if you look at the distance here, as the size increase, the distance is increase. But this L2 caches are the slower than L1 caches, but can have the larger storage space compared to L1 cache. So typically, L2 caches are unified for both the data and instructions, not like L1 cache. The next level cache is L3 cache. The level 3 caches are the largest caches and typically aim at holding all a working set in one. So these L3 caches usually are located outside the CPU, not inside the CPU. Because L3 caches are the bigger in size, so on CPU code, this bulky size memory cannot be accommodated. That's why keeping outside. So based on this, the cache design, let us have a case study as an example. Okay.